Good afternoon and welcome to the 2020 Virtual CROI. This is a special session on COVID-19, which is being broadcast live. The on-demand webcast of this session will be available to the public approximately 1 week after the conference on the CROI website. I'm Wafa El-Sadr, and it gives me great pleasure to co-moderate this session with Dr. Joseph Aaron and Dr. Robert Schooley. I just want to let you know that for today, and only for today, the theme discussion sessions will be starting at 2 p.m. Eastern. As you're all well aware, there's a global coronavirus outbreak that's affected tens of thousands of individuals around the world. It's estimated now there are more than 110,000 people who've been affected by COVID-19 from more than 100 countries. This is the reason why we're having the session today, in order to address some of the critical issues that relate to this outbreak, from the epidemiology, virology, as well as the science and the public health response. I'm glad to introduce our first speaker today, and that will be Dr. Zunyu Wu, and he is currently the Chief Epidemiologist at China Centers for Disease Control and Prevention, and he has been playing a key role in the response in China to this outbreak. Dr. Wu.
Good afternoon. Thank you, Chair, for your introduction. I would like to thank the organizer of the CROI special session on COVID-19 for inviting me to share with you an update on the outbreak of COVID-19 in China. I am very pleased to present to you what we have learned, how we have responded, and where we are now. Slide number 2 shows the early events in the initial outbreak. The initial finding was made by a doctor who received 3 unusual pneumonia patients, all from the same family. Their symptoms and chest images were very similar to SARS. She immediately reported the cases to her local CDC on December 27, 2019. The local health authority started to actively search for cases, and more cases were found. A public health alert was issued on December 31, 2019. And most of these early cases were found to have a common exposure Hualan seafood market. The market was closed on January 1st. We shared information with the WHO and other countries on January 3rd. A novel coronavirus was isolated on January 7th. We shared the sequence with the WHO and other countries on January 10th. And a PCR diagnostic kit was developed and sent to Wuhan for diagnosis on January 11th. COVID-19 was then put on the list of notifiable diseases in China on January 20th. On January 23rd, Wuhan was shut down, and the control sanitaire was put in place for 15 other cities in Hubei in the following days. We responded very fast. Clearly, we all know by now that COVID-19 is very contagious. It is spread very fast. Slide number 3 shows just how quickly we witnessed its spread across all of China. It only took 30 days to spread from 14 counties in one province to over 1,300 counties in 31 provinces. Slide number 4 shows the epidemic outside of Hubei. A majority of cases are either imported from Hubei or a result of close contact with cases from Hubei, which suggests low levels of secondary transmission or community transmission have occurred outside of Hubei. Slide number 5 shows age distributions by sex. There is no meaningful difference between male and female. A majority of cases are adults with 20 to 79 age group, accounting for 94% of cases. Slide number 6 shows the common symptoms we see among COVID-19 cases in China by case severity, mild, severe, and critical. The three most common symptoms are fever, dry cough, and fatigue. Slide number 7 shows the common underlying medical conditions among COVID-19 cases by case severity. A high proportion of critical cases observed among patients with hypertension, diabetes, cardiovascular diseases, and lung diseases. I want to shift gears now and talk about China's response to the COVID-19 outbreak. Coronavirus is a new virus. We have no immunity, we have no treatment, and we have no vaccine, and we have no magic measures to control it. All we used are the basic fundamental public health measures, which include on the slide number 8. Universal population measures such as hand washing and mask wearing, case isolation and management, contact tracing and quarantine, social distancing through suspension of gathering, and community containment via traffic and transportation restrictions, and condo sanitaire. In slide number 9, I want to share some numbers on these measures to give you an idea of their magnitude. Nationwide, approximate 1.4 billion people were asked to stay in their homes, isolating themselves for 10 days during the spring holiday to reduce their exposure and to interrupt transmission. In Hubei, approximate 59.2 million people have been living within condo sanitaire for 50 days now, and this will continue for a while. The number of hospital beds was rapidly expanded from only 2,000 to over 50,000, including those provided by the 3 newly built hospitals and 16 temporary module hospitals. More than 40,000 healthcare workers deployed to Hubei from other provinces to help. Slide number 10 shows the epidemic curve by date of illness onset and by date of case reporting. This data clearly show that the outbreak has quickly been brought under control. We made a rough estimation, used the epidemic in Hubei as a model for the nation, and found that the comprehensive response measures implemented have prevented at least 1 million COVID-19 cases in China. Slide number 11 shows the clinical course from a diagnosis to recovery or death based on COVID-19 cases severity. At onset of illness, some 40% of cases are mild without pneumonia. Another 40% are moderate with pneumonia. 15% are severe, and 5% are critical. During the course of the disease, although some mild and moderate cases progress to severe or critical, a majority are recovered. The current crude case fatality ratio is about 3.7%. Over past 8 weeks, we have learned a lot about COVID-19, which I would like to share with you here. First, transmission dynamics on slide number 12. Majority of cases arise from close contacts of symptomatic cases. 1 to 5% of 38,000 close contacts developed COVID-19, that was observed in 3 areas. Transmission is driven by family clusters. That is about 75 to 85% of clusters. Secondary household attack rates were approximate 10% earlier in the outbreak and fell to 3% with fast isolation. Transmission in closed setting is happening, but is not a major driver in China. Transmission in schools has not been observed. This may simply because of closure of schools during most of this outbreak. Second, slide number 13, nature history. At diagnosis, approximate 80% are mild or moderate, 15% severe, 5% critical. Progression. Approximate 10 to 15% of mild moderate cases become severe, and approximate 15 to 20% of severe become critical. Average time from exposure to symptom onset is 5 to 6 days. Average time from symptom onset to recovery for mild cases is 2 weeks, and for severe cases is 3 to 6 weeks. Average time from symptom onset to death is 2 to 8 weeks. Truly asymptomatic infection is unknown without serology, but appears to be rare using molecular testing, less than 1%. We estimated about 75% of asymptomatic cases at the time of diagnosis soon progress to disease. Children tend to have milder diseases than adults. Third, slide number 14, virology. Virus shedding is highest earlier in the course of disease, compared with the SARS shedding, which peaks at least 5 days after onset. What does this mean in terms of prevention? For SARS, patients wear masks is good enough to stop transmission. For COVID-19, both patients and healthy people need to wear masks in order to stop transmission. Virus shedding can occur in the 24 to 48 hours prior to symptom onset. Virus can be isolated from stool, but there is no epidemiological evidence of fecal oral transmission. Virus shedding usually continues for 7 to 12 days in mild or moderate cases, and for over 2 weeks in severe cases. Patients who recover can be PCR positive after symptoms resolve. This is the end of my presentation. Thank you for your attention. Once again, thanks the organizer for giving me an opportunity to share with you today. Anyone with questions is welcome to contact me directly by email.
And as you can see on this slide, you can see again Dr. Wu's email address, so please direct your questions to him. I'll hand over now to Dr. Schooley, who's going to introduce our second speaker.
Delighted now to introduce Dr. John Brooks. As we all know, the CDC has been spearheading the public health response to the outbreak in the U.S., and one of the people at the tip of the spear is John Brooks, as he has been in many of the other epidemics over the course of his career. So we're delighted to have the opportunity to hear from Dr. Brooks, a capsule of some of the things the CDC is doing to help prevent spread of COVID-19 in the U.S.
Hey everybody, This is John Brooks from the CDC, and I want to thank you and the program organizers for this opportunity to share some of the emerging information about the global epidemiology and prevention of COVID-19. Coronaviruses, or CoVs for short, are a large family of viruses. Of the 7 CoVs known to cause human disease, 4 generally cause mild illness, like the common cold. However, 3 of these pathogens, all beta-CoVs, can cause lethal human illness. These include SARS-CoV, MERS-CoV, and now SARS-CoV-2. So that we're all on the same page, I want to make sure everyone understands we use the term COVID-19 to describe the illness caused by the virus SARS-CoV-2. And it's named SARS-CoV-2 because it is more genetically like SARS-CoV than MERS-CoV. COVID-19 appears to have been first recognized as a cause of human illness in late 2019. We don't yet know exactly when, how, or where this virus arose. We believe it represents a cross-species transmission from an animal reservoir, very likely bats, that may have involved an intermediary animal host. Ralph Barrick will probably speak about this in greater detail in the following talk. Most of the early cases, but not all, were linked to a market in the city of Wuhan in Hubei province, China. However, during 2020, cases rapidly spread to people with no known exposure to this market, presumably through person-to-person contact outside the market, and that amplified the outbreak. By mid-January, COVID-19 had been confirmed in almost every province of mainland China, with the greatest number of cases in Hubei province, shown as the dark pink area in the center of this map. Epidemiologists increasingly use modeling to better understand where an outbreak may spread globally. These types of analyses can help strategically direct and ideally preposition preparedness and response resources. In this example, related to the potential for epidemic of COVID-19 in Africa, modelers combine data on the volume of air traffic inbound to African countries from China on the left, with data on each country's vulnerability to the importation and spread of an infectious disease like COVID-19 in the center map. These data were then combined to generate plots like the one on the right. In this plot, the most vulnerable places are in the upper part of the figure, and the size of each circle corresponds to that country's population size. Circled here in red are the 3 African nations that, subsequent to this analysis, first reported confirmed COVID-19 infections. Although modeling can be helpful, widespread rapid dissemination of infection in our hyperconnected world, as we're seeing with COVID-19, creates challenges to these kinds of prediction analyses. In the 3.5 weeks since the modeling paper I described first appeared online, COVID-19 has spread worldwide with remarkable speed. In this figure from the European CDC, countries reporting confirmed infections are colored gray, and the size of the red dots correspond to case counts. As many of you know, large foci have quickly developed outside China, including major cities or regions in Italy, South Korea, Iran, Japan, as well as on the Diamond Princess cruise ship. This figure shows the daily numbers of new cases reported from China in green, from all countries outside of China in yellow, since January 19th. Early in this epidemic, spread of COVID-19 was limited mostly to China, with 2 large increases in mid-January related to a change in the Chinese case definition. However, as of February the 25th, the daily number of new cases outside China now exceeds those within China, and as of March 4th last week, the number of daily deaths from COVID-19 occurring outside of China have exceeded the number within China. Okay. So now let's move on and review some of the data we know about the clinical epidemiology and transmission of COVID-19. To give you a sense of the relative frequency of the major signs and symptoms observed in patients with COVID-19, I'm showing here these data from 3 reports of hospitalized patients in China. More than 80% of patients develop fever during illness, over half develop cough, about 25% myalgia or arthralgia, and a small fraction develop headache or diarrhea. Although fever is the predominant sign of illness, one report observed a much lower prevalence of fever at presentation of only 44%, even though most of the patients eventually developed fever. These signs and symptoms of COVID-19 are consistent with what we often call flu-like illness. Unfortunately, at this time, no particular set of signs or symptoms or related clinical findings can reliably clinically discriminate COVID-19 from other respiratory viral illnesses such as influenza. Most people present with subacute or acute onset of cough and fever. Fever may be measurable, but as I noted earlier, not all patients have a measurable fever at presentation, although they may describe feeling feverish and then later go on to develop a fever. I also want to highlight that there have been some reports of persons presenting with isolated GI illness, specifically diarrhea, that has preceded the development of cough and fever by a day or two. The median incubation period is currently estimated to be 4 to 6 days, with a range of 2 to 14 days. Most people will recover spontaneously with supportive care. But for those who develop further illness, those complications may include pneumonia, respiratory failure, and multi-organ system failure. In terms of the age distribution of persons with COVID-19, these data from the largest Chinese surveillance report to date show that most patients have been middle-aged adults who also comprise a large portion of the general population. I want to make special note of what appears to be very limited amount of SARS-CoV-2 infection and COVID-19 illness in children. Data pending peer review and that were published online last Wednesday suggest that children are equally susceptible to COVID-19 as adults, at least adults under age 50 years. If true, then the data presented here in this figure likely represent underreporting of pediatric infections. This kind of underreporting may be due to a decreased likelihood that children will present for clinical care because we know they experience milder illness than adults, or that if they come to care, they may not be recognized as having COVID-19. Adults, especially adults over age 60, experience significantly more severe COVID-19 illness and are more likely to die, as reflected by these case fatality rates, or CFRs, shown by the yellow line and y-axis to the right. I caution against fixating too much on precise values, since a number of factors can affect the CFR, such as the geographic location where illnesses are occurring in the local healthcare system, or the group of patients affected by illness. Two factors I want to highlight are these. First, the number of people tested. In outbreaks, the most evidently ill persons with a higher risk of death tend to be tested first. As more people with less severe disease are tested, the increasing number of total cases will include more survivors and thereby lower the CFR. Second, the number of deaths. How many people die depends on how quickly illness is recognized and how well it can be managed. Deaths will be higher where sufficient life-sustaining supportive care is lacking. Our current best estimate, which admittedly has a large range at present, is that all things considered, the case fatality rate is likely somewhere between 0.5 and 3.5%. By comparison, the CFR for seasonal influenza is about 0.1%, meaning that COVID-19 could be 5 to 35 times more deadly than seasonal influenza. Despite the important concerns about case fatality rates, most COVID-19 illnesses are, and we expect will continue to be, mild, and most patients will recover spontaneously with some supportive care, especially younger and middle-aged adults and children. Okay, let's turn to transmission. Respiratory secretions are the main mode of COVID-19 transmission. Infection is spread through respiratory droplets in the air and that land on surfaces. Transmission from persons who are pre-symptomatic or who may have asymptomatic infection is possible, but the contribution of these infections to overall numbers of illness appears to be small at this time. Stool is unlikely to be a source of infection. Although viral RNA is readily detectable by RT-PCR, there's only one report of replication-competent virus having been cultured from stool, and no cases of infection where exposure to infected feces is the sole mode of transmission. There have yet been no observed transmissions perinatally of COVID-19, and COVID-19 viral RNA has not been detected by RT-PCR in amniotic fluid, cord blood, neonatal throat swabs, or breast milk. We also know that the amount of virus shed from the respiratory tract of infected, ill people is greatest at the time symptoms start, then declines. What this means exactly in terms of the presence of infectious virus has yet to be fully worked out and is a major focus of our work at CDC. For those of you familiar with HIV viral load but new to CT values, think of them as the inverse of each other. CT values, or cycle thresholds, represents the number of PCR cycles it takes for the test to detect the presence of viral RNA. Lower CT value means it took less time and that therefore more viral RNA is present in the sample. I'd now like to turn to talk about high-risk groups. Persons with medical comorbidity and advanced age are at increased risk for severe illness and death. In the Chinese data I showed previously, persons with cardiovascular disease, diabetes, or chronic respiratory disease had case fatality rates greater than 5%. Unfortunately, there aren't data available at the present time about persons who were immunocompromised whether by medical therapy or acquired infection. But for persons with HIV, we think the risk for severe illness would be greater for persons at lower CD4 cell counts and who aren't virally suppressed, since we've seen this same pattern in other intercurrent illnesses in people living with HIV. Nonetheless, all people with HIV should take precautions against this new virus about which we're still learning a lot. And I want to note that CDC estimates that equal to or more than 50% of people with HIV are over 50 years old. The data around pregnancy are generally reassuring. Current observational data only exist for women infected in the third trimester because we've only been seeing this infection for a couple of months. However, maternal morbidity among women with COVID-19 appears to be similar to that of uninfected women without COVID-19. And as I noted previously, there has been no definitive evidence of infection transmitted perinatally. I'd like to take the last couple of minutes to review some issues around preparedness and prevention. For some of you, the basic concepts of pandemic preparedness may be new. The purple curve in this figure shows the hypothetical number of cases over the course of a pandemic. Although different groups like CDC and WHO may divide pandemics into different phases, we all approach them with the same two main strategies: contain and mitigate. As a potential pandemic is recognized and cases rise, efforts focus on containment or doing the very best we can to stop or at least slow the early spread of infections. But as transmission outpaces containment efforts, we move to a mitigation strategy focused on managing illness, which Tony Fauci will speak about later, as well as preventing new infections with a variety of non-pharmaceutical interventions, such as closing schools, teleworking, and canceling or postponing large social events. Right now, I would say most areas of the U.S. are at least in the early initiation or acceleration phase, climbing up the curve, and that some communities are close to pivoting to mitigation, if not there already. Non-pharmaceutical interventions, or NPIs, that focus on social distancing are applied in the home, at school, at work, and at gatherings. If you'd like to read more about these in detail, you can go to the website I've shown below. Individuals can also take personal action to prevent transmission of COVID-19, action that will both help protect you from giving it and from getting it. I know you've heard these before, but they bear repeating. To the extent that it is under your control, avoid close contact with people who are sick and avoid touching your face. Also, wash your hands often with soap and water for at least 20 seconds. Hand sanitizing gel is okay when soap and water are unavailable, but studies clearly show that washing with soap and water for 20 seconds is best. So for those of us with hands, I just want to say be nice to them. Give them a good bath a couple of times a day, and they'll keep taking good care of you. Those of us affected by and working in HIV know that stigma is the enemy of public health. There is, unfortunately, growing evidence that the kind of stigma with which we are very familiar and often have lived experience is now affecting people who are perceived as being at risk of spreading COVID-19, especially Asians or persons of Asian descent. This is a photo of graffiti confronting anti-Asian COVID-19 stigma from Italy. I think the artist's voice resonates with what we have known since the early 1980s. Note the message in French on the front of the box the woman is holding. #Je ne suis pas un virus, or I am not a virus. Sound familiar? I encourage all of us to use our rich collective experience with HIV to help fight anti-COVID-19 stigma. Lastly, I'd like to touch on some recommendations for people with HIV as regards COVID-19. Ensure an ample medication supply. I'd recommend having 30-day supply available at all times. Keep vaccinations up to date, especially vaccinations against respiratory illness like influenza and bacterial pneumonia. Establish a plan for clinical care if isolated or quarantined. Look into telemedicine options or physician online portals. And lastly, maintain a good social network, but maintain it remotely. Social contact helps us stay mentally healthy and fights boredom. So in closing, I'd like to share this image with you from my local dollar store, and thank you for your attention. Take good care of yourself and remember that there's plenty of soap.
Thank you very much. Dr. Brooks, for this excellent presentation. I want to encourage all of the audience to please continue to send your questions to the email address or to the of the speaker or the email that you can see here on this podium. We will also have Dr. Barrick, who's going to be speaking next, available online to take live questions. So keep that in mind as well. He will be available after he presents his presentation. Dr. Aaron?
Great. I have the great pleasure of introducing Ralph Barrick. He's a professor of epidemiology and microbiology at the University of North Carolina, and he is certainly one of the most prominent coronavirus virologists, I think, in the country and probably in the world. I've heard this talk a couple of times. It gets better each time, and I'm really looking forward to it.
I'd like to thank the organizers for inviting me to come and present an update on SARS coronavirus. Next slide. The talk today will focus on giving a brief review of emerging coronaviruses with a focus on SARS, to discuss the outbreak of the SARS-2 epidemic, talk about the origins of the virus, its genome organization and relatedness, and the type of disease that it causes. And then I'm going to talk briefly about countermeasures. And obviously, as you look on the right side of the slide, there have been 4 major respiratory emergence events in the 21st century, including 3 coronaviruses and the 2009 H1N1 influenza. Next slide. Coronaviruses have a long history of cross-species transmission. Starting about 100 to 800 years ago, 4 of the human contemporary coronaviruses, of which 3 are shown here, including NL63, OC43, and 229E, emerged from bats or animal origins to cause outbreaks of human disease. In the last 20 years, there have been 4 major coronavirus emergence events, including SARS coronavirus about 16 years ago in 2003, MERS coronavirus in 2012, about 7 years, a porcine epidemic diarrhea virus in 2012, which arrived here in the U.S. from China, SARS coronavirus, which emerged recently in China, and is worrisome because it can also replicate efficiently in human cells about 2 years ago. And finally, the SARS-2 coronavirus about 3 months ago. So there's been an accelerating cross-species movement of these viruses in the 21st century. The major drivers of coronavirus evolution include a regulated fidelity machine. This involves a protein called NSP14, shown here in blue, which gauges the NSP12 RNA-dependent RNA polymerase, shown here. The NSP14 3' to 5' exonuclease removes 3' mismatches from the growing template strand and provides a way for RNA proofreading. However, changes in environment or protein-protein interactions can alter the fidelity efficiency, providing a mechanism for rapid evolution in changing environments. In addition, coronaviruses undergo high-frequency RNA recombination, so that during the replication as the polymerase is moving down the strand, template strand, the polymerase can fall off and bind to the template of a heterologous strand to produce chimeric recombinant molecules that have genetic material from each of the two parents. Next slide. The other major driver of evolution is the plasticity of the surface glycoprotein shown here in blue, and this is the actual structure that has been published about 2 to 3 years ago. This S-glycoprotein tolerates high rates of mutation. It can tolerate deletions and insertions that can alter tropism and anagenicity. The modular design of this spike glycoprotein allows modular evolution where component pieces can be exchanged between strains, and this affects host range, tissue tropism, and transmissibility. Next slide. SARS coronavirus has its origin here in the tree in yellow. These are the strains that emerged in 2003 from bats to open markets with civets as intermediate hosts. You can see here this is the Urbani strain of SARS coronavirus, and a series of related early, middle, and late phase epidemic strains, as well as civet and raccoon dog strains shown here in yellow. Detailed phylogenetic analysis and metagenomic sequencing of bat populations have revealed 2 additional classes of SARS group 2b coronaviruses. These include the strains down here in light pink. These strains cannot use human ACE2 as a receptor and are low-risk strains in terms of their capacity to replicate in human cells. In contrast, strains up here in pink are considered high risk. They can use human ACE2 receptor for docking and entry. They can replicate efficiently in primary human airway epithelial cells. And so there is a large reservoir of SARS-like strains that are present in bats that are poised for trans-species movement. This was the current state of the knowledge before December 2019 when SARS-2 emerged. Now, the mechanism by which SARS emerged in 2002 provides insight into how the SARS-2 virus emerged in 2019. The closest relative to SARS is a bat virus called WIV16, which is about 97 to 98% identical to the epidemic SARS strains, and there are 2 possibilities leading to the outbreak. One is virus spilled directly from bats into humans, and these humans in the open market infected civets, setting up a transmission cycle between civets and humans, or alternatively, bats infected the intermediate host civets, which then provided a transmission a pathway for infecting humans in open markets, setting up a transmission outbreak. Ultimately, SARS caused about 8,000 cases and 774 deaths in 32 countries, and went extinct in human populations by early 2004. But is it extinct, or are there viruses, bat viruses in the bats and other animals that are still a threat level to human population? Well, one of the approaches that we use to address this question is shown here. So we developed a reverse genetic platform, a DNA copy of the SARS coronavirus molecular clone. This is a mouse-adapted strain, and the little arrows here represent mouse-adapted mutations. And here are related SARS viruses, SARS group 2b coronaviruses that have been discovered in bats. So our basic approach was to take the spike glycoproteins from these strains, like WIV1 or SHC014 or WIV16, and replace the Urbani spike with these bat spikes. And when you do these, you find 2 classes of viruses, two classes of spike genes that exist within this group 2b coronavirus phylogenetic tree. WIV1, WIV16, and SHC014 range from about 97 to 90% identical to the SARS spike. And all of these can program efficient infection of primary human airway epithelial cells down here, which have been obtained from discarded lungs from transplant recipients. In addition, the ones in the box can use the human ACE2 receptor, just like SARS. And then we synthesized the full-length genomes and recovered the full-length viruses, and they had the same properties in terms of their capacity to replicate in primary cells. So consequently, this led to the following hypothesis, that the SARS-like coronaviruses, including the MERS-like coronaviruses, exist as large heterogeneous pools of related viruses in bats and bat species, of which there are about 1,300. They can vary in terms of their spike variation by up to 35%, And in 2003-2004, SARS coronavirus emerged from this reservoir to infect humans and cause a large number of cases globally. But future outbreaks could easily be seeded by strains that are 10% or even up to 35% different and cause future outbreaks in human disease. And in fact, that's what happened in December of 2019. SARS-2 is about 22% identical. Is 78% identical to the original SARS virus that emerged in 2003. It's caused almost 110,000 cases globally with about 3,800 deaths in over 70 countries. It's actually about 110 countries right now. And currently the case count rate in the United States is about 538, recognizing that we don't have sufficient diagnostic tests to determine the true number of infected individuals in the United States. Human-human transmission is rampant and is occurring in multiple countries, including Germany, US, Thailand, Japan, China, Iran, Vietnam, and elsewhere. This results in the following hypothesis, is that the known SARS group 2b coronaviruses include a number of strains that are poised for human emergence, and those are shown here sort of in this encyclopedia of high-risk strains. We have SARS down at one end, which we use as one end of the bookcase. And then you have strains like WIV1, WIV16, and SHC014 that vary up to about 10%, with the SARS-2 strain at about 22% variation in the spike. Notice that there are still a large number of strains that haven't been identified, and these are all considered high risk because they use human ACE2 receptor for entry, they grow in primary human airway epithelial cells, they can cause acute respiratory distress syndrome either in humans or in animals. They all display an age-related disease severity, so as with increasing age, either in humans and animals, there's more severe disease. And as you pass about the 10% variation rate within the spike gene, these strains begin to escape existing immune therapeutics. And so for that matter, agents that were primarily developed against SARS will probably have little impact on controlling SARS-2 infection and pathogenesis. The availability of these strains provides a platform to test broad-based vaccines, human monoclonals, and antiviral drugs that can be used and placed on a shelf to control future outbreaks. This is not relegated only to the group 2b coronaviruses. MERS is a group 2c coronavirus. Although most of the high-risk strains in the Encyclopedia of High-Risk MERS-like coronavirus strains have not been identified. There have been two that have been, MERS down here, which we use as one baseline, and a virus from China called MERS 422, which is about 35% different in a spike-like a protein. This virus is fully capable of replicating in primary human airway epithelial cells and using the human dipeptidyl peptidase 4 receptor for docking and entry. So these are both high-risk strains, and a similar encyclopedia exists for these viruses as well that can seed future outbreaks. So this changes our current paradigm for how zoonotic viruses emerge from animal populations. The old hypothesis was that most of the zoonotic strains are not poised for trans-species movement, but a rare mutation occurs, let's say in this virus right here. And then a second rare or random event occurs. The virus actually comes in contact either directly with humans or with some secondary animal reservoir, where the virus begins to replicate and adapt to that new reservoir species or directly into the humans. These then can be transmitted to humans for further adaptation and back and forth to set up a transmission cycle, or down here, in both cases requiring additional mutations to mediate that, followed by a third round of mutations that drive epidemic outbreak. So this is a fairly rare event that requires multi-step mutations to mediate the emergence of an epidemic strain. Our data suggests that as bats are becoming more compressed within hibernacula, generalists exist within the population. And these generalists exist because multiple bat species with varying bat ACE2 or DPP4 receptors are in the same hibernacula, so generalists or viruses that can use receptor orthologs across different bat species begin to emerge, and then this zoonotic population is now seeded with pre-programmed viruses that have been designed to use multiple bat ACE2 receptors, and by random chance, some of those can actually directly use humans or secondary reservoir hosts. And so you don't need this massive mutation-driven adaptation process to initiate the infection. And in some cases, these viruses may be capable of programming directly to the epidemic strain. So SARS coronavirus, SARS-2, emerged in early December in Wuhan, China. Began as a cluster of cases associated with open markets that were described in December 31. At that time, the Chinese reported that there was no evidence of human-to-human transmission. It was not very pathogenic, and it was not SARS coronavirus, although it was likely a novel virus. And I think the major lesson here for every government of the world is never underestimate the epidemic potential of an emerging virus or the damage that it can do to both to your population or your economy. The Chinese closed the Wuhan open fish market in early January 2020. They identified a SARS-like coronavirus on January 7th. It was a distant relative to SARS coronavirus, or a kissing cousin. And its genome length sequence was reported from 5 isolates between the 9th and 11th of January. 15 healthcare workers were infected and described by the Chinese research community, demonstrating person-to-person spread around the 20th of January. This is a table that includes important updates about and comparisons between SARS-2 and the earlier emerging human coronaviruses, SARS coronavirus and MERS coronavirus. And let's just focus on the categories that are blocked off in red. If you look at the number of cases, SARS-2 has been in over 70 cases, actually around 110 countries globally, much more prevalent than either SARS or MERS. Many more cases as compared to SARS or MERS, although the mortality rate is less. And about 17 U.S. states have reported cases as we go through this presentation today. Importantly, the mortality rate averages about 3.4%. And another important feature is to remember that about 83% of the cases are mild or asymptomatic. Another thing to remember is that mortality rates are age stratified, so that if you are over 80, the mortality rate is about 14 or almost 15%. Between 70 and 79, your mortality rate is about 8%. Between 60 and 69, it's about 3.6%. Between 50 and 59, the mortality rate is 1.3%. And if you are less than 40 years of age, the mortality rate is about 0.2%, with pretty much no one dying under the age of 15. The main incubation period is about 5 or 6 days, but it can range up to 14 days. The RO, or the number of people that are infected from one individual to another, is about 3, and that super spreaders and asymptomatic and mild spread are common with SARS-2. Asymptomatic or mild spread is rare with MERS and was not almost never described with SARS. The major cause of death from all of the emerging coronaviruses is acute respiratory distress syndrome. This is an end-stage lung disease with about a 30% mortality rate should you develop it. About 17% of the patients with SARS-2 require respiratory assistance, 13% with invasive ventilators, and there's very little evidence of secondary infection. So what happens with acute respiratory distress syndrome is here's your normal lung, oxygen flows down into the alveoli and diffuses across this interstitial barrier to be picked up by red blood cells. MERS, SARS, and SARS-2 destroy these single cells lining the alveoli, allowing for fluids to flow across the interstitial bed and fill up the alveoli with pulmonary edema, and hence the cause of death could be drowning because you can't, because these balloons in essence become water balloons. That's not the end of the disease. The repair process involves a profibrotic response, where fibroblasts can be laid down during the repair process, leading to a multi-cell layer thickness between the alveoli and the capillary bed, preventing oxygen diffusion over into the capillaries, and this could lead to death by suffocation. So the major causes of mortality are hypoxia, oxygen insufficiency, leading to multi-organ failure and death. And importantly, infection in children are very mild, and males generally develop more serious disease than females. And then children in generally can have very high virus titers. Now, the drivers of the SARS epidemic included animal markets where civets and raccoon dogs could transmit to humans. The hospitals were the epicenters for viral disease because healthcare workers became infected, and super spreading events were common in hospitals. These could be tailored by barrier nursing, and transmission typically occurred with SARS between 24 and 36 hours after disease onset. Community spread was limited, and there are very few asymptomatic cases, and so this was very vulnerable to contact tracing and quarantine. In context, SARS-2, we don't know what the animal reservoirs are, so we can't call the animals that are transmitting to humans. Although hospitals still remain epicenters of disease expansion, barrier nursing hasn't proved as effective as we'd like, since there were about 1,700 healthcare workers infected in China. And community spread and with asymptomatic cases are very common with SARS-2. So this confounds quarantine and contact tracing. So it's going to be very difficult to control the SARS-2 outbreak. Now, once the sequence was obtained, it could be compared to what was known in terms of the other group 2b coronaviruses. You saw this slide before. Here's the SARS strains here in the middle, the low-risk SARS-like bat strains down here, and the high-risk bat strains up here. The new 2019 novel coronavirus called SARS-2 is about 25% different in its genome. It has over 6,000 nucleotides changes compared to these other strains, and it represents a new clade. This is called clade 1. The SARS-related strains appear in clade 3. So these viruses are completely different in terms of any other. We'd never seen SARS coronavirus, group 2b coronaviruses like this before in the past. The closest relative to SARS-2 is this RATG13 virus. It's a it was a virus sequenced from a bat in a cave in Yunnan province in China in 2013. It's 96% identical, which means there's about 1,200 nucleotides different between this strain and this strain. Again, quite different from these earlier SARS-like strains that have been described over the last 15 years. The genome organization of the Wuhan coronavirus, or the SARS-2 coronavirus, is shown up here. These are the replicates. The rectangles in green are the structural proteins of the virus, and the boxes in gray are luxury ORFs. And you can see that SARS basically has the identical genome organization. The spike-glycoprotein of SARS-2 and SARS both bind the human ACE2 receptor. There's the ACE2 receptor up here in green, and the SARS are the SARS-2 receptor binding domains in the spike-glycoprotein down here, and you can see there's a very nice interface between SARS-2 and the human ACE2 receptor. In fact, it makes a better contact with the human ACE2 receptor as compared to the original SARS coronavirus strain. There are 14 contact interface residues in the spike of the receptor binding domain that bind human ACE2 molecules. And up here are the SARS and the SARS-related strains and the high-risk bat strains that are shown here. Everywhere there's a green residue, it's highly conserved. If it's light green, it's partially conserved. As it turns to red, it becomes more deleterious in terms of being able to engage the human ACE2 receptor. And all these strains here can efficiently use human civet bat and mouse ACE2 receptor. Even the SHC014 strain that has 7 to 14 differences. Here's the receptor binding domain of the SARS-2 viruses from Wuhan. You can see that it has 8 of 14 contact residues in common with SARS. It encodes a couple residues that are common with the SHC014 strain, and then it has a large number of unique residues encoded within its receptor binding domain. In contrast, strains that are low risk have deletions within the receptor binding domain, as shown here and as shown here. I mentioned that these were the spikes were anagenically quite different, with up to about 22% variation. Here's the SARS spike shown here. Anywhere there's a green residue indicates variation, and you can see that the early, middle, and late phase 2003 epidemic strains are almost identical. They're very closely related to civet and raccoon dog strains. Here is the intermediate host, as well as the WIV16 virus, which is its closest relative. But as you move more towards the anagenically distinct, the strains with more genetic variation, you can see that the SARS-2 strain is encodes a significantly increased amount of antigenic variation on its surface as compared to the original SARS strain. There's a variety of vaccine complications with SARS. The first problem is that vaccine efficacy in general was reduced in age populations, and that can reduce performance. The heterologous group 2b SARS coronaviruses that exist within the zoonotic pool can vary by as much as 35%, and that means that vaccine strains that are tailored to a single serotype within the group 2b coronaviruses will likely not provide protection against the more variable strains. Of most concern is that the original SARS doubly inactivated vaccines that were purchased by the NIH and adjuvanted with alum caused a Th2 immune pathology after vaccination, especially in age populations. In some cases, these vaccines actually increased mortality following challenge. And they occurred not only with the doubly inactivated vaccine, but also with adjuvanted spike glycoprotein vaccines. Most of these adjuvants drove a Th2 immune pathology, so although SARS coronavirus again is quite different in its spike glycoprotein, using the right adjuvant that drives the Th1 response might be absolutely critical for performance. There's also some evidence of enhancing antibodies, although there's some controversy around this that has been shown in primates and in cell culture. Whether this is a major problem in vaccine design, we don't know. So these are these are concerns that the vaccine community is going to have to address as we move forward with vaccine testing. Our own group has been involved in looking at therapeutic interventions for the coronavirus family. There are no approved drugs, immune therapeutics, or vaccines against any group 2b coronavirus. We've been working with experimental drugs that target the NSP12 RNA-dependent RNA polymerase in collaboration with Gilead. And so Gilead provided us a fairly large panel of nucleoside inhibitors, of which remdesivir proved to be the most potent. This is the structure of the prodrug remdesivir GS5734, which causes chain termination during RNA synthesis, and it targets this protein NSP12 right here. The work that I'm going to talk to you about is done in collaboration with, mostly done by Tim Sheehan and Amy Sims here, and Rachel Graham in my laboratory, as well as collaborators at Vanderbilt University as part of a center grant that's run by Rich Whitley at the University of Alabama. So we've tested remdesivir in primary human airway epithelial cells, the normal target for virus infection, and you can see that remdesivir, as you increase the dose of remdesivir, you can block MERS coronavirus replication in HAE cultures, MERS RNA synthesis in HAE cultures, SARS replication in HAE cultures, and SARS RNA synthesis in HAE cultures with very potent IC50 values of sub-micromolar concentrations. Importantly, remdesivir also works against all of the contemporary human coronaviruses. I've only shown NL63 here. It works against precursors to the MERS coronavirus strain that are 25% different. It works against the most antigenically distinct zoonotic bat group 2b coronaviruses, HKU3, and it works against the pre-epidemic, the high-risk strains that are poised for human emergence, SHCO14 and WIV1. I should also say that GS5734 also inhibits SARS-2 replication in cells and culture. In animals, GS5734 diminishes SARS coronavirus disease both in mice and in primates. This is mouse data showing that in vehicle-treated animals, they'll lose about 20% of weight by day 4, but remdesivir-treated animals, either prophylactically or therapeutically, are significantly protected. And there is significant changes in virus titer between vehicle-treated animals, shown here at prophylactic or therapeutic conditions, versus drug added prophylactically or therapeutically. So because it works against all known human coronaviruses and zoonotic and epidemic human coronaviruses, as well as SARS-2 in vitro, with the in vivo experiments are ongoing right now. In fact, Gilead is clinical testing remdesivir for COVID-19 disease at 5 randomized control trials in hospitals across the globe, including study designs that look at a treatment of severely infected patients and mild or moderately infected patients in Wuhan, a double-blind placebo-controlled study in the U.S. by the National Institute of Health, as well as severe and moderate trials that are going to be tested globally in the near future. Our group has also identified another nucleoside inhibitor drug called audD 1931, which is under FDA review. The manuscript is also under review. It works against both the SARS-2 virus and all SARS and MERS-like strains that have been and human contemporary strains that have been tested in our laboratory, both in vitro and in vivo. And we've tested both of these drugs against the SARS-2 strain. So with that, I'd like to acknowledge people in my laboratory, especially Tim Sheehan, who is an independent scientist at UNC, and his group, Rachel Graham, Amy Sims, Alexander Schaefer, Lisa Grilinsky, and others who were involved in these studies. Our good collaborator, Mark Dennison's group at Vanderbilt University, was integral to all the drug studies that I talked about, and we've been very fortunate to have this collaboration with Gilead scientists. The 1931 drug is done in collaboration with George Painter at Emory University, and much of this work is supported by an NIH Center grant that's run by Rich Whitley out of the University of Alabama. With that, I thank you for your attention.
Thank you, Ralph. That was terrific. There is the potential to ask Ralph questions, to ask Dr. Barrick questions. He's going to be online after Dr. Fauci's presentation. You need to send those questions to croyroom312@gmail.com, which is on the screen. Well, it's not on the screen right yet, but it will be in a second. Also, Ralph, Dr. Barrick's email is also up on the slide, or it just was. And here is the email. It's also been on the slides, I think, while Dr. Barrick was presenting. So, Wafa, should I leave it to you to introduce, or Chip, Dr. Fauci?
Yes.
Thanks very much, Joe and Wafa. We're now going to move to the biomedical response to this virus in the U.S., which is being led by the NIAID, and we're delighted today to have with us the director of the NIAID, Dr. Tony Fauci, who is well known to all of us.
Good afternoon, ladies and gentlemen, friends and colleagues. First, I want to apologize for not being able to be with you in person today, and I want to thank you for giving me the opportunity to make this presentation by video. The subject of my talk, as you know, is the research response to COVID-19. I say a view from NIAID, but there are really a number of other things going on in other venues. If one looks at how this all started with regard to research, it was when the Chinese revealed the draft genome of the virus that was implicated in the Wuhan pneumonia outbreak. Putting the sequence on the public database opened up the door for a series of studies, some of which I'll have the opportunity to describe to you today. These are the four general areas that we will be discussing. First, in the arena of basic research, the development of animal models, and the development of research resources for researchers. This is really very important because what we want is to get a significant number of individuals who have already been involved in coronavirus research, as well as people with new ideas who have not yet been in this field. With regard to animal models, we're exploring small and large animal models. We've been given supplements to the animal model experts to spur model development. As with work that we have done in other arenas, the development of good animal models are always important. In addition, we're supporting intramural researchers, including those involved in our biocontainment labs, which will be playing an important role in our endeavor. And we're putting out task orders for contract work for countermeasure developers on the outside. This is the phylogenetic analysis of the SARS coronavirus 2. As you see, it was in the realm of the beta coronaviruses. Obviously, it's very important to have gotten samples that people can work with for every aspect that they do, from diagnostics up to therapy. Viral isolates and reagents were made available to the research community by the BEI Resources Contract. It's a World Reference Center for Emerging Viruses and Arboviruses at the University of Texas Medical Branch. We know now that we can get resources, samples, isolates, and others to individuals, hopefully, as we go further into this in a timely manner. This is just one example of some of the extrapolation of the basic fundamental research that has been done with other pathogens, including HIV, in which we did a number of experiments leading to the surge in viral vaccine research with HIV, is namely the application of structural biological approaches, including cryo-EM. This is a paper that appeared just a little while ago in Science, delineating the cryo-EM structure of the 2019 novel coronavirus spike as it exists in the pre-fusion conformation. Diagnostics obviously of great importance. The ultimate goal is to make available a wide availability of diagnostic tests for state and local health departments and hospital centers. The state and local health departments were given early on diagnostics from the CDC, which I'll get into in a moment. As many of you know from the publicity it's gotten, there were some missteps there, and there was a delay in getting tests out. The solution to this would be to alleviate the regulatory requirements and allow individual centers as well as companies who have a history of developing diagnostics to produce diagnostics to the tunes of millions and millions, so that physicians who need diagnostics will have it available, as well as using it to determine in a surveillance way if there are undetectable detections in the community, which would be an indication of community spread. In addition, we desperately need serological assays, which, as I speak, are already being developed for serosurveillance. As I mentioned, the CDC very quickly, again related to the publication of the sequence on the public database, developed an RT-PCR, which I mentioned just a bit ago, for the public health sector. The NIH has been developing additional diagnostic tests, PCR-based assays, and ELISA assays, and NIH-supported researchers from Hong Kong University have developed the molecular diagnostics and published their protocol on the WHO site, and has distributed these reagents to 12 countries to enable them to perform diagnostic assays. Moving on to therapeutics. There are antivirals, monoclonal antibody, and other agents are being developed and tested in real time, literally as we speak. One of them that I'm sure you heard about is remdesivir, which is the nucleotide analog, has showed some promise in coronaviruses and animal models. Interestingly, the protease inhibitors contained in Kaletra, lopinavir, and ritonavir, as well as interferon beta, have been used investigationally in other coronaviruses. I'll say a bit more of that in a minute. But just to mention, there are other broad-spectrum antivirals which have activity in vitro and may actually be used in clinical testing, including chloroquine as one of them. There'll be drug screening and targeted drug design, as well as monoclonal antibody that are being isolated and tested. These are a couple of the papers showing the preclinical evidence of remdesivir as a potential for treating coronavirus infection. You're going to be hearing, or you will have already heard from Dr. Barrick, who's been a main leader in this, and I'm sure you're going to hear a lot more about that, or have heard a lot more about that. In addition, the rhesus macaque model publication was interesting from Heinz Fellman, in which he showed both prophylactic and therapeutic capability of remdesivir in the non-human primate model. If you look here at the display of International Clinical Trial Registry, the platform, as of just a few days ago, on March 3rd, 2020, there are over 260 records for these kinds of clinical trials. The NIH itself has begun a clinical trial of remdesivir and has done that in the trial on participants who are Americans who are repatriated after being quarantined on the Diamond Princess cruise ship. That study is an adaptive study to evaluate additional investigative treatments and to enroll participants in a number of sites, which I'll show you on a map in a little bit. In addition, the Chinese have 2 large studies measured in several hundreds of patients, which is a randomized controlled trial of remdesivir versus remdesivir together with point of care, as well as point of care alone. In addition, as I mentioned just a moment ago, the Kaletra approach has shown some clinical benefit for SARS patients and will be now extrapolated in a clinical trial in the novel coronavirus. And then finally, there are vaccines. There are a number of platforms, technologies that are in development for the COVID-19. I'm going to just mention one of them, but also refer to several others. The one in question that is coming from the NIH, and by no means is this the only one or may not even be the best one. We just don't know at this point. But what we're doing is a messenger RNA platform in collaboration with the company Moderna. The production has been fast-tracked by Moderna, and GMP product for clinical trial was shipped to the trial sites in February. What we're going to be doing is from the time the sequence was up to the time we go into clinical trial will likely be somewhere between 2 and 3 months, I believe closer to 2 months. And if so, it would really be the fastest, I think, of any situation in which we've gone from sequence availability to clinical trial. To show you the comparison of vaccine that came out of the Vaccine Research Center, and that obviously a number of others are doing this, the first time we used a DNA platform, and remember the one we're using now with the novel coronavirus is an mRNA platform, but if you look at the time from sequence selection to going into a human in phase 1, it was 20 months for SARS, 11 months for H5N1, 4 months for H1N1, 3.2 for Zika, and probably 2 months or maybe even less for the novel coronavirus. Actually, as I mentioned, this is really at record speed, but there are multiple candidates that are being pursued by a number of organizations. So you're going to be hearing literally, I guess, week after week and month after month of a number of candidates. These are just some of the ones that are in development. A chimpanzee adenovirus vectored vaccine from the RML, the Rocky Mountain Laboratories, in collaboration with Oxford. A recombinant protein from Baylor College of Medicine with Peter Hotez and his colleagues, as well as a number of additional concepts by pharmaceutical companies, biotech companies, and others. These are some of the clinical research sites, which is the old vaccine and treatment evaluation units, which have now been put into a consortium with a leadership group. These are some of the sites in which the domestic trials will occur. In addition, as I mentioned, the University of Nebraska, which has the repatriated individuals who are infected, as well as the unfortunate outbreak that we're seeing around the Seattle area. With regard to current funding opportunities, we have a notice of special interest regarding the availability of urgent competitive revisions for research on the novel coronavirus to improve our understanding, to develop medical countermeasures, and as I mentioned earlier, to develop animal models. In addition, and finally, there are the 2020 NIAID Omnibus Broad Agency announcement that solicits development of any of a number of platform technologies as well as candidates themselves to develop vaccines. So, in summary, I've given you just a bit of a snapshot on the kind of research response that's emanating out of the NIH, specifically NIAID. This is a rapidly evolving field, and we look forward to meeting the challenge of what would be, I think, a very important impact on global health with this evolving epidemic as we live through it in real time. Again, thank you for the opportunity to come to you as a video, and I wish you a very successful meeting.
Thank you very much, Dr. Fauci. And for the audience, you can see Dr. Fauci's email on the screen. Please do send questions to him directly if you are interested. I want to just let the audience know that this session will be available right at the end of the session on the CROI website. So I need to correct myself, within 2 hours. Now we're fortunate to have Dr. Barak with us, and so he will be able to answer some of the questions that you have sent live. For other questions that we've received, and we received quite a few questions, we will try to triage them to the specific speakers after this session. But Dr. Barak, first question is, would it be possible to develop a serologic test for SARS-CoV-2?
Thank you, and it's a pleasure to be here to answer questions for the audience. The simple answer to that question is yes. SARS-2 has extensive variation in the N-terminal domain of the spike glycoprotein that can be used as a type-specific response. Antibodies are also targeting that region. And so a simple serologic test based on the first 300 amino acids, 500 amino acids of the spike glycoprotein would be quite sensitive and specific for the SARS-2 coronavirus. I do want to mention one other point of clarification. As I was listening to myself talk, the vaccine complications that I described are in animal models, not in humans, both in mice and in primates. And I think that's important to remember. SARS vaccines were only tested in a phase 1 trial with this limited number of individuals in the US, and that was, to my knowledge, the only human testing that was ever done.
Thank you very much. The second question actually relates to the first question, the availability of serologic tests to do prevalence studies and so on. So the second question is, does a person develop immunity after surviving a coronavirus infection? And can a person who has had an episode get reinfected or have more than one episode?
So there's interesting data on that from both SARS and SARS-2 infections and in MERS infections. There were some sporadic reports of individuals who seroconverted with MERS and then returned to baseline after infection, including some who were RT-PCR positive. So the possibility for this happening it certainly is possible, although I do not think it's frequent. There was also some evidence of a chronically infected MERS patient, although there was only a single one to my knowledge. Mm-hmm. In the case of SARS-2, there are sporadic reports in China of individuals who experienced an acute infection, were released after they'd resolved infection, and then reportedly have become infected again. But I don't think there's anything that's been officially published. So it's an emerging story, and we have to pay attention to it.
Thank you. The third question is, what about reservoirs in the body for this virus, similar to, for example, in HIV or Ebola? Any information on any reservoirs?
At this time, at least I'm not aware of any known reservoirs for either SARS, MERS, or SARS-2 infection in human hosts. Viral genome persistence can last quite a while in sputum samples. But whether those are associated with replicating genomes or not is certainly not clear. Of course, part of the problem was there were insufficient samples of SARS globally to follow sufficient cases to ask questions along the lines of long-term persisting viral genomes and where they may persist. Certainly this outbreak is of sufficient scope to reveal those types of rare infection events, much like they did with Ebola.
And the next question is regarding what happened to SARS-CoV virus. Is it still circulating in a limited manner, or has it disappeared completely?
I think most people that work with virus discovery, the people at EcoHealth, Dr. Shenli Shi and the Institute of Virology in Wuhan, and other sort of virus hunters all agree that SARS is a bad virus. SARS-2 is also a bad virus. There are 1,300 different bat species, at least, that exist on the planet. We've only surveyed maybe 50 to 75 total species for the presence of coronaviruses. So most people think that SARS, the original 2003 strain, is still out there. It's circulating in bats, and it's waiting for its moment in time.
And another question is about the ACE2 receptors, and are they differentially expressed in humans, either quantitatively, anatomically, or by ethnicity or by age in humans?
So ACE2 is on a sex-linked chromosome. It's expressed at higher levels in females than males. As you age, the expression levels of ACE2 decrease. ACE2 has been shown to play a protective role against influenza-induced acute respiratory distress syndrome. And so there is probably a direct relationship to the levels of ACE2 expression and disease severity, and it probably plays some contributing role to the age-related disease phenotype that's seen in humans. However, there are certainly other major factors that contribute to the age-related disease distribution, including immune senescence and overall reduction in both B and T cell responses as a function of age.
And building on that question, what about ACE inhibitors? Another question. Are they possibly a viable option to block this virus?
There was a very nice paper published by a group whose name I forget, in 2013 or 14, that demonstrated that several ACE2 inhibitors had fairly good activity against SARS. And so I think it's a very good idea to go back and re-explore the use of these drugs, both in vitro and in improved animal models of human disease.
The next question is about transmission and the whole issue of whether there's airborne transmission in addition to droplet transmission of this virus. Can you elaborate on the possibility of airborne transmission and any evidence to support it and its contribution to transmission of this virus?
So during the SARS outbreak in 2003, I think it was called Amory Gardens outbreak was associated with aerosolized feces that had high concentrations of SARS in it, that infected not only a large number of people in that hotel, in that high-rise community, but also individuals in nearby high-rise communities, demonstrating that you could have airborne spread of the virus under the right conditions, which are somewhat unappealing to think about. In general, I would argue that I think the majority of data argue that it's large droplet transmission and contact with virus on fomites is the major mechanism of spread.
Thank you. Last question is a question regarding EIDD in 1931, and what type of a drug is it, and where is it available?
It's a cytidine, a nucleoside inhibitor. It was developed. It's being mostly developed by Emory University by a fellow named George Painter, and he can certainly provide lots of information about that drug.
Thank you very much. I think these are all the questions we've received. We've received many other questions for the other presenters. And again, feel free to continue to send your questions, and we'll triage them too. Go ahead.
Ralph, I'd like to ask you this association between hypertension and severe disease, and the fact that SARS-2 uses the ACE2 receptor. Do you think that's just coincidence, or do you think there's something going on there?
I have a tendency not to believe in coincidence. I think it needs to be explored in more detail. I've thought it needed to be explored in more detail for quite a while.
Great. Well, thank you very much, Dr. Barrick, and thanks to co-moderators, and thank you to the audience who are watching this session. And recall that this will be available on the CROI website in about a couple of hours. Thanks again.